Hello, my name is Shogo Tokunaga, and I'm a student at Chuo University. Today, I'd like to talk about scour around the monopile. This is today's content. I'm going to divide my presentation into 5 parts. First, I'd like to start our introduction. When installing offshore wind farm facilities in shallow water, embedding foundation pile in the seabed is often used. However, this method has some problems due to weather and sea conditions. For example, such as erosion and scour of columns, the cause of scour is the influence of wave and current flow. Next, many studies are being done to solve the problem of scour around the monopile. I'd like to start talking about previous research. Summer et al. Shows that scour depth depends on the Kc number and proposed a relational formula. Chin et al. Found that greater the Kc number, the scour depth becomes more resonant, and that the position of maximal scour depth changes from the left and right of the pile to the back. In numerical analysis, Umeda et al. Analyzed the scour process around the monopile. They analyzed the scour terrain development process, shape, sand ripples, eddy currents, other current field using a newly constructed numerical model. Previous studies on vorticities state the following. Petersen et al. Investigated what vorticity around the monopile affects scour in experiments. Umeda et al. Reproduced the vortex because the bed shear stress increases and the influence of vortex and contraction around the monopile. Suzuki et al. Conducted experiment of scour behind vertical seawall and examined the relationship between the overflow and the scour depth. It's known that the vortex has a great influence on the scour depth. In the experiment, investigating how the scour around the monopile changes when the Kc number changes by giving current field and wave. In the numerical analysis, investigating how the current field and vortex around the monopile, which cannot be understood in the experiment, affect the scour. However, there is no example of quantitatively evaluating the effect of vortex flow on scour around the monopile. So this is my purpose. We quantitatively evaluate the relationship between the vortex, the scour depth, and the scour position around the monopile due to the difference in the Kc number using numerical analysis. This is our study flow. Next, I'd like to start talking about the numerical model. We use the CAD-MAS BCM developed by Arikawa et al. CAD-MAS BCM is a model that incorporates the building cube method into a 3D numerical wave channel. The building cube method was developed by Nakahashi and Kim. The calculation area is divided according to simple rules. It has features such as good compatibility with parallel computers. Figure 1 shows a grid comparison between the nesting grid and the building cube method. But the building cube method shows high definition at any location. It's possible to set up a calculation grid for. CAD-MAS South 3D, developed by Arikawa et al., structured mesh Navier-Stokes simulator is a further extension of the 2D numerical wave channel calculation method. Next, I'd like to start talking about the previous experiment and our analysis. This picture shows the outline of the previous experiment. Chin et al. Conducted an experiment using an experimental channel with a length of about 450 meters, a height of 12 meters, and a width of 5 meters. We performed the numerical analysis modeling this channel. This is the computational conditions. Cubes are arranged in all computational domains up to level 0 to 5. However, the cubes were not divided in the z direction. The grid cell size was set at equal intervals. This table shows the calculation conditions. The farther away from the monopile, the closer the grid size. Next, I'd like to start talking about the result of our analysis. This is a movie of the current velocity field on the bottom. The most important point is the local current velocity generated around the monopile. This shows the average current field around the bottom of the monopile. You can see that the current velocity field is generated around the monopile in all cases. Also, the spread of the current velocity field increases as the Kc number increases. It can be seen that a wake vortex is generated on the downstream side of the monopile and the current velocity is decreasing. This slide shows the vorticity in each direction on the bottom based on the average current velocity. You can see that the z-direction vorticity is large around the monopile. Therefore, we examine the relationship between the z-direction vorticity, the scour depth, and the scour position. This figure shows the series number based on the average current velocity. It can be seen that the value of the series number increases around the monopile. And this figure compares the series number around the monopile and the vorticity. It can be seen that the value of the series number also increases where the vorticity is large. This slide shows a comparison of the counter diagram of the scour depth for each case in the experiment, and the counter diagram of the calculation vorticities. It can be seen that the maximum scour depth increases as the Kc number increases, and the position of the scour depth also increases. The vorticity also moves downstream as the Kc number increases. There is no difference in each case on the transverse direction. The Kc number was calculated from the calculation result of the current velocity in each case and compared with the experimental value. You can see that the Kc numbers are almost the same in all cases. This slide shows the relationship between scour depth and vorticity on the streamwise direction and the transverse direction. In this case, the Kc number is the smallest, and it can be confirmed that the scour depth is also the maximum, where the vorticity is the largest. The following shows the case where the Kc number is the second largest. As in the previous case, there is a tendency for the maximum scour near the maximum vorticity on both directions. In the case with the largest Kc number, the same can be confirmed on both directions as in the other two cases. But on the transverse direction, there is a position where scour occurs with small vorticity. In the streamwise direction, the larger the Kc number, the larger the z-direction vorticity. In the transverse direction, as the Kc number increases, the correlation between the z-direction vorticity and the scour depth decreases. From the figure below, it can be seen that the y direction vorticity increases in the transverse direction. It considers that the y direction vorticity due to the horseshoe-shaped vortex has a large effect. This slide shows the relationship between the vorticity and the scour depth in each case. In all cases, the scour depth tends to increase as the vorticity increases. It can also be seen that as the Kc number increases, both the vorticity and the scour depth increase. And the scour depth cannot be evaluated on z-direction vorticity. It's also necessary to consider x and y direction vorticity. When the vorticities in all directions were combined and compared with the scour depth, scour occurred at the vorticity of 0. It's necessary to examine the vortex around the monopile in more detail. This slide shows the case deleted where the vorticity is 0. Even if the case where the vorticity is 0 is deleted, scour occurs at the position where the vorticity is small. It's necessary to consider scour at the point where no vortex is generated. Finally, conclusion. It was found that the z-direction vorticity is largest around the monopile, and that the z-direction vorticity increases downstream as the Kc number increases. In the streamwise direction, it was confirmed that the scour depth increased as the z-direction vorticity increased. In the transverse direction, as the Kc number increases, the correlation between the z-direction vorticity and the scour depth decreases, which is considered to be affected by x and y direction vorticity. It's necessary to consider scour at the point where no vortex is generated. Thank you for your attention.